Okay, welcome. Many have asked how to do simulation from Quartus II. Uh, Many were in the impression that we need QSIM for the simulation, but for simple simulation like this, the built-in simulator is more than sufficient. First we have to type in our code, uh, and then we have to press compile. Initially, I commented these two lines, attributes keep and these two lines, because I explain the reason later. So let's go ahead and compile this first. Okay, the compilation was successful. uh, then we to verify the design, we could use what we call the RTL viewer. To do that, we have to go to tools, netlist viewers, and then to RTL viewer. This shows the logic diagram of our circuit. Don't worry about this. This is a buffer actually. This helps to get the signal, but basically our circuit is like this. Okay, so the block diagram seems right. Now we have to create the signal file. Since this is a multiple inputs here, this block has multiple inputs. We cannot just simulate by providing one waveform like we did in multisim. So we have to create a special waveform file. uh, so since this is a gated SRLH, we have to model truth table of the uh, model the inputs from the truth table of this SR latch into a waveform file. So we have three inputs and one output. So we just have to model these three inputs. So we have 8 states. Uh, yeah, the combination of these three inputs. Uh, so first we need to go to file and create a new waveform file. So file new, and then we need to select vector waveform file and then press OK. Okay, again. This is the waveform area. First we need to load the signals from our design uh, to the waveform file. To do that, we have to go to edit, insert node or bus, and then we could manually add nodes here. But since we have a compiled design, we could use this node finder to get the signal from this SR latch file. Uh, so we could go to the node finder and then press this list button, and this shows the signals, and then we could click this to import, and then we could press OK and OK again. So this loads up the signals. uh, this is in not the right order. It works, but for the convenient purposes, we could since the truth table is like clock, set, reset, and then q and stuff, it's better to order the list in that order. First comes the clock, then comes the set, then the reset. So RG and SG are intermediate signals. Those comes in the middle, and last comes the key. We could select the signal we need to move and drag and drop where we want. Okay. So clock is first signal, S is second signal, R is third signal, and these are intermediate, and this is output. Okay. Then we need to model these inputs from input states from the truth table to our signal file. Okay. I'm taking one state, one interval as 10 nanoseconds. So this state spans for 10 nanosecond, this state spans for 10 nanosecond, totally 80 nanosecond wave. Okay, first we need to click this waveform editing tool. Then let's see, in the first instance, okay, before editing the waveform, one crucial thing we need to do is zoom out this view, since there is 18 nanoseconds worth data here. We cannot see it all in one glance. We have to scroll this, so it's better if we could zoom out this. To do that, we have to go to view and zoom out. Since there is a shortcut, control shift space, I'm going ahead and use that. Control shift space, I'm pressing it several times. Okay, so we could get a clear view from 0 to 80 nanoseconds. Okay, uh, then we could click this waveform editing tool, and then let's pull up our to the really quickly. First instance, the all these three signals should be 0. Okay, initially you can see these signals are held low. That's okay. The next instance, E is 0, S is 0, R is 1. So R should be 1 in this time span. To make this high, we could click from the beginning and drag till the end and release, so it becomes high in this time period. And the next instance is 0 1 0, so set becomes 1. And the next instance, 0 1 1, this is 0, this is 1, this is 1. Okay, first half is done. The next instance, set is 1, sorry, the clock is 1, set is 0, R is 0. Other instance, say clock is 1, R is 1, clock is 1, R is 1. Then next instance, E is 1, S is 1, E is 1, S is 1. Then after that, all three are high. Okay, now we are done with the waveform. We could go ahead and press Ctrl S to save this file. And also when saving, it's better to save this waveform file in the name of the file we are going to simulate, the VHDL file. So name of the VHDL file is sr_h. I'm naming the waveform file as also sr_h, and then we're gonna save it. Okay. Then we have to go to the simulator tool. To do that, we have to go to processing and select simulator tool. Then this keyword prompt, I'm pressing the do not show this again. This says it's better to use model sim, but do not care. Okay, then the simulator window comes out. I'm going to maximize this so we could see it clearly. So in the first section there is this simulation mode. So initially we are going to do a functional simulation. Functional simulation doesn't take account this propagation delays and stuff, but timing simulation takes those things into account. So we first doing a functional simulation. I think you can remember I commented these two lines because it gives a error when doing a functional simulation with these two uncommented, because these are intermediate signals, and it's only useful for the timing simulation. So for the functional simulation I'm going to comment this, and for the timing simulation I'm going to uncomment this line. Okay, and the next important thing is the simulation period. We could run simulation until all vector simulations are used, but like for like rule of thumb, I'm defining an end simulation time. If we look at the signal, our simulation starts at 0 and ends at 80 nanoseconds. So we select 80, we type in 80 nanoseconds as the end simulation time. Then another special thing is override simulation input file with simulation result. What this does is, after ticking this, uh, so this edits the waveform file and fills in these outputs. If you can see, these intermediate signals are and outputs are not defined because it only fully defined after the simulation itself. So okay, then in the functional simulation we should press this generate functional simulation netlist first. It takes some time. Okay, functional simulation netlist generation was successful. Then we could go ahead and press start. Okay, simulator was successful. Then if we click this srlash file, it says uh, this file was updated. Do we need to load the save changes? So we could press yes. Okay, so in this state we could see, if we, okay, when e is 0, these outputs are latched, means the previous input is held. So since the previous input is not defined, we are starting the simulation from 0 picoseconds. So like q is not defined at that state, so it shows it's undefined. But if a signal is present before this latch starts, it shows that previous signal. So yeah, this is correct. Then we are concerning about this after the fifth state. That means uh, e is 1, r is 1. So when clock is 1 and clock is 1 and reset is 1, we could see the q is 0. Okay, that section is checked. And then e is 1, s is 1. E is the clock is 1, s is 1, r is 0, the q is also 1. Then the last state, all three are 1, 1, 1, 1, and the output is 0 according to this. So the simulation result seems legit. And let's do a timing simulation. To do a timing simulation, we have to go to select the timing simulation mode, and it's better to uncomment these lines and compile this again and then go to simulator tool and select the timing and run the thing. But I'm not going to do that right now. So okay, all is well. Go ahead and press start. So if we check the timing result, it shows like this queue is bit delayed. That's probably because that this timing simulation take into account this propagation delay. So okay, according to the lab sheet, it says to do, for the first task, it says to do both functional and timing simulation. Okay, that checked. So basically we have to repeat the same for these other two parts. I'm hoping to cover this part 4 and 5 in the next video, if time I get time. So thanks for hanging around.